So now we want to talk a little bit about how light and matter interact, because this is going to. So now we have a basic understanding of light. Depending on how it interacts with matter, it's going to help us get an understanding of matter. So one way that light and matter interact is by matter radiating light or emitting light. So if I heat up a solid, if I just take some chunk, whatever the material is, and I heat it up, depending on the material, heat is an increase in temperature, right? So what happens to the substance when I increase the temperature? Temperature is a measure of average kinetic energy of the particles, or the average molecular motion of the particles, right? So that motion includes vibration, so the particles and their bonds stretching and contracting or just vibrating. It includes rotation, rotational motion, so turning and flipping in space, and translation, which is traveling in space from point A to point B. Right? So we know solids and liquids experience all of these motions. I'm sorry, liquids and gases experience all of these motions, but solids, the particles are held tightly enough where they're not sliding past one another, they're not flying through space undergoing translational motion. They're probably just vibrating there in whatever positions they're organized in the solid. But they have some kind of energy, right? Everything has at least vibrational energy. And so if I heat that up, basically I'm supplying the collisions I need for the molecules to start moving faster and faster. And so what we find is some of that energy, that kinetic energy that the particles have, can be converted into light. And so this was just an early observation that gave us some idea that energy is quantized, or that because the type of light that's emitted comes out in specific energies or specific quantities of energy, that means that this interaction between light and matter, it's not a continuous thing. It's something that happens in steps or in specific quantities, right? So if I heat, another way to think about it, I think there's a, no, there isn't. There used to be, I don't know where that went. There was a picture, but I mean, you can imagine this in your mind. If you take a chunk of metal and you heat it up, eventually it might glow red, right? Or it might glow white or blue, depending on the temperature, depending on the metal, right? So if you have this thing and you heat it up, this hot metal, if you see a specific color, that's telling you that specific wavelengths of energy are being emitted, right? So not every possible wavelength might be emitted, and so that's what we mean by quantum. We're not getting every possible value, only certain possible values or certain possible quantities of energy are coming out. And so you can call these quantities packets or bundles, but that's one of the behaviors of light. And since that light came from the behavior of the matter, that also gives us some sense that matter might be quantized, or matter might only be possible for matter to exist at certain quantities of energy as well. So that basically, that idea that energy is quantized rather than continuous, I mean, that can be likened to a piano. If you're going to play a piano, you can only play notes that are matching up with whatever keys you're hitting on the piano, right? I can't play the note in between two keys that are next to one another, because there's only certain notes that the piano can play. So that's a quantized instrument. And light kind of has a similar behavior. There are certain energies that the light won't exhibit. So here's another experiment that illustrates that. This one probably illustrates it much more effectively which is why I want to spend a little bit more time on it than the other one. And this is the photoelectric effect. So basically what we're doing here is we have a chunk of metal, we hook it up to a battery. So this metal here is not touching this rod in the middle. Okay, so those are close to one another but not touching. So the negative charge comes from hooking it up to the negative end of the battery, and then the rod is hooked up to the positive end of the battery. All right, so this is not a circuit. If I connected these two metals, like if I took a wire from the rod and connected it to here, what would happen? I would just make a circuit, and all the electrons would flow through that wire, and I would have a complete circuit. Right? So it's not what I'm doing. I'm not making a circuit here. What this experiment involves is a buildup of negative charge here and a buildup of positive charge here. Okay, because the battery is the supply of electrons. It pushes extra electrons onto this thing, and they build up there, and it pulls electrons off of this thing, and so I have a lack of electrons on that side. Why don't the electrons just fly through space and get to the positive charge that's attracting them? They're not touching. I mean, they can see each other. They're close enough. I mean, they're pretty close together. If I build up enough negative charge, you might create an arc here, and the electrons might jump over. Okay, so that's something we're not doing. So we have some negative charge there. We're not building up a huge amount of negative on that site, though. So if we don't create so much negative that they jump over, that must mean that whatever atoms make up this metal have enough positive charge in their nucleus to hold those electrons in. So I have extra electrons, and that repulsion makes it a little bit unstable, but it's not so unstable that the electrons that are there break away from all the positives in the nucleus and fly to the other side. So we're setting this up this way, and when we add light and we hit this thing, what we find is that affects this meter. I don't have quite as high of a voltage because I create some electrons that can jump off of this metal and fly to the other side. So what does that tell us is happening with the metals? What conclusions can we draw from that experiment? So one thing that tells us is the negative charges that build up here have a certain energy associated with their attraction to their metal that they're initially on, right? So the electrons on this metal feel an attraction to the nuclei in those atoms. And that attraction has a certain amount of energy associated with it. When I add the light energy basically collides with those electrons and breaks that attraction. So that means that gives us a sense for how strong of an attraction that is, right? That means that attraction is probably not a really strong attraction. If I set it up with a different metal, so if I go from sodium to zinc to platinum, I will find that different quantities of energy are necessary, right? So that tells me that the electrons in an atom have certain quantities of attraction holding them in. So there's this threshold frequency. That means if I hit this metal with certain types of light, nothing will happen. Once I get above a threshold and I increase the frequency or decrease the wavelength enough to get the wavelength short enough where there's enough energy associated with that light, then when I shine it, electrons will get popped out. So there's a certain quantity of attraction associated with those electrons. So this simulation here does a good job of illustrating this concept as well. Okay, so this is the same thing This side, this is where my electrons are built up. That's the metal where the electrons begin, right? And they have some attraction associated with the nuclei that make up those atoms. And I'm connecting it to my battery here. And the electrons can't just jump over because the protons in these nucleus are holding those electrons in. Right? So I'm going to shine light. So let's shine some light here. Oops. Pull this over and start shining some light. So when I increase the intensity, what am I actually doing? What? Right. I'm increasing the brightness of the light or the amplitude of the waves or the number of photons that are coming through. I'm not changing the energy per photon, and I'm not changing the number of packets of energy in a given amount of space. I'm not changing the wavelength. I'm not changing the frequency. So this represents. So if I'm on this 850 nanometer end, is that the high energy end or the low energy end? So 850 nanometers, if I go in the other direction, I'm going down in nanometers. So the higher the nanometers, the higher the energy? No. The higher the nanometers, the longer the wavelengths, the lower the energy. So at this point, I'm talking about long wavelengths. And if the energy is low, does that have enough energy to break the electrons' attractions with the atoms that are in there? No. So it doesn't matter. It doesn't matter how high I crank up the intensity. That is a low energy form of light. Yes?
So when an electron is turned into a photon, does that affect its charge?
So the electron is not turned into a photon.
Okay.
Okay, so what in this experiment, the photon, the energy of the photon gets absorbed by the electron, and if the energy is not enough, nothing will happen. Nothing happens to the energy. Nothing happens to the electron. And that's what we're seeing right here. Right? So if the wavelength is too long, there's not enough energy, no matter what the intensity, nothing will happen. There's no result. If I lower the wavelength, there's a threshold where eventually I start to knock electrons out. Okay, so the electrons are not being converted into photons. The photons are not being converted into electrons. What's happening is the energy started in the form of light. It gets absorbed by the electrons and converted into kinetic energy. Potential energy and kinetic energy. Right? So initially, these atoms over here, right, there's a nucleus, and the electrons are outside that nucleus, right? There's a certain amount of attraction that those electrons have to that nucleus. The light energy, some of it gets converted into potential energy as you break that attraction for the electron and it leaves. That's higher potential energy for the electron because now it has the potential to go ahead and move over here and get attracted to a positive charge. So some of the light energy gets converted into potential energy, and then if I have enough intensity beyond that, that extra energy gets converted into kinetic energy for the electron as it's traveling through space at a higher speed, right? So if I lower the intensity here, then the electrons, well, you can't really see it too well here, the electrons come off at a much lower speed. Well, I made the intensity 0, so that's not going to work. But if I lower the intensity, the initial speed of the electrons is slower. So even with low intensity, this nanometer here represents a wave that's much shorter in wavelength. So now I have enough energy to break that attraction. There's a certain threshold where I have to have the light to have that threshold or higher to break the attraction that the electrons have and increase the potential energy of the electron. So the light energy gets converted into potential energy for the electron. So that's sodium. And sodium, let's bring the intensity back up. Oh, come on. Get this out of here. So where is the threshold for sodium? That's not what I want to look at. Let's see. So for sodium, the threshold is roughly right around here and here somewhere. At 565 nanometers, it's not enough energy. Right? No matter where I put the intensity. If I lower the energy a little bit, if I increase the energy a little bit by lowering the wavelength, then I have enough energy to start knocking electrons out. So the fact that there's a threshold tells us that the electrons in the atoms have certain quantities of energy associated with them. I have electrons that have this quantity of attraction, and I need a specific amount, a specific quantity of potential energy to break that attraction. And that potential energy comes from the light. So this also tells us about the quantum or quantized nature of electrons. They exist with certain energies and certain energies of attraction with their nuclei that they have. So let's just look at one more here. Let's change it to platinum. Okay, compared to what you know about sodium versus platinum, since we know sodium has loosely held outer electrons and platinum is one of these precious metals, it has the ability to hold its electrons pretty tightly. It doesn't rust, it doesn't corrode because it holds its electrons relatively strongly. So if we change this to platinum, we look at the same energy, what happens? Nothing. So the threshold for platinum is much higher. To knock platinum's outer electrons away from its nucleus, it takes a lot higher energy. So to do that, I would have to lower the wavelength more and more and more. Even outside of the visible region, I've got to get higher and higher in energy to the point where, okay, now I reach the threshold for that metal. So every metal has its own threshold, and the fact that there's a threshold tells us that the energies of the electrons are quantized. It tells us that the electrons have a specific quantity of attraction to the nucleus that holds them. Questions about that? Okay, so you want to make sure you understand about that threshold frequency or threshold energy that's necessary to break that attraction. So this is also important. The number of electrons ejected is proportional to the intensity. Right? So if I don't reach the threshold energy or the threshold frequency or wavelength, I won't get any electrons ejected. But once I get past that threshold, then if I increase the intensity, I'm just pushing more electrons out in a given period of time because I have more photons to knock those electrons away from their initial attraction. And then we can use this equation if we wanted to quantify how much energy there is holding the electron in. So let's look at this next one here. This one is very similar. Let's see. Yeah, this one here we're looking at hydrogen. So here's one atom of hydrogen here. And in this case, this is a little bit different. We're looking at a slightly different threshold. So here in my atom of hydrogen, I've got my nucleus and I've got my one electron. Right? So we're looking at hydrogen as a very simple atom. Just like in the case of the metal, in the other experiment we're just looking at with the metal, there's a certain amount of energy associated with that electron, right? It's attracted to the nucleus to a certain extent. So if I want to break that attraction, I need a certain amount of energy. I can supply the energy in a form of light, but what we just learned is I would need to have a certain wavelength associated with that light if I want the energy to break that attraction. Another way to break that attraction is with an electron. So if another electron is flying around and it comes in here and collides with that, the kinetic energy of that electron, instead of light energy, the kinetic energy or motion of the electron and the force of that collision can knock the other electron away from the nucleus. So this is another experiment that you can do, that scientists have done, where we can vary the energy or the speed of this electron and see what happens. So let's fire an electron at this thing and see what happens. Oh, I got to apply some voltage here, or the electron's not going to be attracted. Whoa. So when I modify the voltage here, this changes the speed that the electron comes at that atom with, right? And that's because when I increase the voltage, I'm creating basically a stronger battery, and I'm creating more more positive charge on this side. So when my electron is on the other side and it experiences that positive charge, it's going to fly over there really fast if I have more positive charge, right? So if I apply a small voltage here, I can fire electrons all day at this thing. Nothing will happen. Why is nothing happening? Right. The energy associated with this attraction, if the electron comes in with less energy than is associated with that attraction, it can't knock the electron out. So just the electron that I fire at that atom just passes through. There's nothing, it doesn't do anything. So what will happen if I increase that energy? And so you can look at this table. This is the energy I'm at right now. I need to increase that energy above a certain threshold, right, associated with that attraction. So if I increase that energy by increasing the voltage here above that threshold, notice what happens here. What's the explanation for this? What's happening to the electron? So this electron that comes through to the other side here, that's the original electron. That's this one that I shot at the atom. What's going on with the atom with the electron that started in the atom? This one here. What? Yeah, it's emitting light. It's not getting knocked out. So this experiment shows me something else. It shows me that not only do electrons have a certain amount of energy required to knock them out of an atom completely, like the last experiment we just saw showed us, it also shows that electrons have a certain attraction holding them in, and it is possible, if I have just the right quantity of energy, that I can knock them away from the atom but not totally out of the atom. So that is an extremely important experiment, a very key experiment that is almost all of the way we talk about and understand the behavior of atoms is based on this. The fact that electrons can be in a certain energy level, a certain degree of stability due to their attraction to the nucleus, and if I don't have enough energy to overcome that, nothing will happen. But there are certain quantities of energy I can hit that electron with that will knock it a certain distance away from the nucleus. But then if it feels the attraction to the nucleus still, it's not out of the atom completely, the electron will move back down. And that's what this chart is showing. The electron gets promoted up to this level, and then it's still in the atom. It's not knocked out completely. If I want to knock it out completely, I need even more energy. And my electrons that I'm firing at that atom don't have enough energy right now to knock the electron out of the atom completely. So if I just knock it up to this higher energy level, so-called level 2, what will happen? Well, it'll be attracted again, and it will move back down to energy level 1. So what is causing these photons to be emitted? This is a situation where I'm not starting with any light, but light is emitted. How is the light created?
The energy released by the electrons.
Right. So this is a potential energy scale. What I have here is low potential energy. That's the ground state. The ground state is always the lowest possible potential energy for whatever particles I have in a system. And so this number 2 here, this is an excited state. That's a higher energy state. So the initial energy required to make that jump comes from the electron I'm knocking into the atom. Once I move my electron that started in the atom up to that level, now it has a higher potential energy. And when I go from high potential energy to low potential energy during the relaxation, anytime I have high potential energy and then later I have less potential energy, I can't just destroy that energy from existence. It has to go into some other form, and that is the light. So during that relaxation, light, the potential energy gets converted into light energy. And so if I increase the voltage a little bit more, now I get 2 different forms of light energy emitted. I get this purple photon and the blue photon. And you can see, and this chart here shows well, you can't see that. It just charts what wavelengths those photons actually have. I'm only getting very specific wavelengths coming out because they're only very specific quantities of energy that the electron can get promoted to. This is the quantized or quantum nature of matter. This is the fact that electrons have certain energy levels. I can't promote the electron to energy level 2.5. It doesn't exist. If I don't have the right quantity of energy to excite that electron with, the electron won't do anything. Only certain quantities of energy will excite the electron. So that's the key take home here. If I were to have, this is a pretty cool thing, if I were to have a bunch of atoms and I kept firing high energy electrons at them, eventually you'd see this quantum behavior right here. There's certain wavelengths emitted and other wavelengths, this entire area and this entire area, there's no light emitted with those wavelengths. So that means I cannot excite the electron in any of these atoms to a level that's associated with that specific energy. There are only certain energy levels where the electron can be. I encourage you to fool around with these, if you're curious about them. Any questions about this? Yes?
What if you knock all the electrons off? Is that a particle that doesn't have any electrons?
Yeah, so if that's a great question. If you supply enough energy, that's a really good question. So you have these atoms and they have electrons. They're held in by a certain attraction. So we know if we supply, there should be, at least theoretically, some threshold where we could overcome all the energy. And you can do that if you supply enough energy to these atoms and knock all their electrons out, then you get what's called a plasma. So plasma is like the 4th state of matter. If you take matter and you get like a really high temperature or a really huge amount of energy and knock all the electrons out, then you just have the electrons like not in atoms, but they're just there, and the nuclei are just there. That's a plasma. Good question. Any other questions? Yes.
What
What?
makes the electron emit different colors?
Yeah, so I should have mentioned that. Let me explain that. So what we just said was, try to erase this. So this is happening really fast here. Maybe I'll stop this so it's not distracting. Stop. Or I could just do this. So I'll stop firing electrons at that stuff for a minute. So if I don't supply any energy, all the electrons are in the ground state. Right? So the reason there's a whole bunch of gray circles here is because I've got a bunch of atoms. Each atom has its own electron. So all the electrons for all the atoms are represented there. So if I supply enough energy to break this attraction and it goes to energy, and I supply that exact quantity of potential energy, then the electron will be up here at this higher potential energy. Once that occurs, it'll feel the attraction and it'll move back down. So it will release, so I'll do red for emission, it will release or emit this exact quantity of energy that's associated with this specific wavelength. Right? And this is a low wavelength because this is a high energy gap. That's a large quantity of potential energy associated with that specific transition from n equals 2 to n equals 1. Now, if I were to hit these electrons with a larger quantity of energy, and instead of knocking the electron up to n equals 2, I were to promote it to n equals 3. Now, once the electron is here, it may not relax all the way back down to the bottom right away. Or it might. If it does, that releases an even greater quantity of energy, and that's the next one that's right here. But once I excite it above n equals 2, there's a decent chance that it might first relax from 3 to 2, and then later relax from 2 to 1. So if it goes from 3 to 2, that's this wavelength. That's the purple one. So the different wavelengths there result from the different possible transitions from a higher potential energy to a somewhat lower, somewhere along the way, other potential energy. So it has to be, to emit light, it has to be a relaxation from high potential energy to low energy. And then this is pretty much the quiz question, so I might as well just say it now. For hydrogen to emit light in the colored region, so UV is outside the colored region, IR is outside the colored region. To emit light in the color region, just for hydrogen, there are 4 transitions. This purple one is the lowest wavelength. That's the highest energy one. So that's the largest energy jump in the visible region. That would be from 6 to 2. 6 to 2 is a higher quantity of energy than 5 to 2 or 4 to 2, right? So the 5 to 2 is slightly less energy, the 4 to 2 is less, and the 3 to 2 is less. Right? So this 6 to 2 one is the purple, and the 3 to 2 one is the red. If I go from 2 to 1, that's too much of an energy jump to be in the visible region. That's in the UV region. If I go from 6 to 5 or from 5 to 4, that's too small of an energy jump to be in the visible region. That's in the infrared region.